This is episode 4 of Advent of Code 2021. In this one, we're looking at days 10 to 13. So please enjoy and let's just get to it. So today we're starting with day 10. I think this is a common recurrence in Advent of Code that there is usually at least one task based on balancing brackets and braces. And this year is no different. So we would have input that would consist of lines, and each line would have a bunch of brackets, braces, parentheses, and angled brackets. And our goal would be basically to say which lines have errors in them, as in which lines the brackets are not balanced. So basically every time we would leave a bracket or any kind of these brackets, if we were not in such a bracket, like if that was not the innermost bracket, then we would have to basically exit and mark the line as broken. Additionally, we should keep the bracket that actually caused the syntax error, as these would be scored differently. For example, the usual parenthesis would have 3 points and the square bracket would have 57. And the final result of the first part of the task would be the sum of all these points for every line. So every line would have one of these at most, because it could have been a valid line, but if it's invalid, it would have one of these. We would assign each line some score and sum it all up together. At first, I didn't really know how to do this correctly. I didn't want to pull in any kind of parsing library, because this seemed easy enough that we could do this manually, like just trying to parse the string by myself. And at first, I wanted to just fold on the characters of a line, starting with the state with like every kind of bracket would have 0 points, and I would increase the points of a specific bracket once I entered that bracket. And if I ever had negative points, that would be a failure. But this was not the right way to go, because these brackets could be embedded in a different kind of bracket, and then we would basically have to reset, like temporarily reset the score of such a bracket. So basically every time we entered the bracket, we would have to basically reset the scope of previous brackets, or at least the ones that were different from the one that we were currently looking at. So if we were looking at a square bracket, we would need to reset the scope of how many nested, like normal brackets or parentheses we were in. But as we'll see in a couple of minutes, there was no point in like differentiating between brackets, as its own scope would be good enough. One thing I wanted to do was try to parse every line to either a failure, which would be basically the character that broke our string, so definitely one of the closing brackets. And in the successful case, it would be an option of result, where result would be like a car that opened the bracket and a list of other results, so things that were embedded in that bracket. I played around with different ideas of how to parse each line, but eventually I settled on doing a stack. So all of this really resembled function calls in a programming language. When you enter the function, you would be within that function, and all the other functions that were on top of it, that were basically calling this function, would be further down the stack, the call stack of that function. This is really something completely different, but the idea is the same. Like we could have a stack, in this case it would be a list, because Scala lists are actually stacks. In that stack I would track which brackets I am in as a sequence. So the top entry on that stack would be the most nested bracket that I'm currently in, so the one that I just entered. And the idea was that I would go with every character in my input, and if I saw one that was opening a bracket, I would add that bracket on top of the stack, and I would move on to the next character. But if I found a character that was closing a bracket, I would have to see the top of the stack and check whether it's a matching character. If it wasn't, I would just fail immediately, like I'm closing a bracket that I have not opened recently. But if the top of the stack was the opening of the same kind of bracket that I was currently closing, I would remove that element from the stack and continue with that new state. So basically the same kind of state that I had before entering the current bracket, although I would already, skip some characters, because I'm now at the point when this bracket was closed. This whole idea could probably have been implemented as a traverse on the lists of characters in the input with something like a composition of state and either, but I did that in previous days, in the previous tasks. You can see that in the previous videos, and I didn't want to do the same thing again. And also, to be honest, I didn't think of it until now. In the first implementation, I made some extractors for openers and closers, so basically the characters that were allowed to open and close a bracket respectively. But later I replaced these with predicates that were just used as guard expressions in a pattern match. And the core abstraction that I was using here was the state data type. So that held the stack, so the current brackets that we were in, and also the remainder of the string. So I had basically three methods on my state. One was push, which would add an element to the stack and also get to the next character in the remainder of the string. Then we had pop, which would take the top element of the stack and return a new state with that element removed. And it would also move to the next character in the string. Finally, I had uncons, which was just operating on the string. It would check whether the string is empty. If it was, it would just return none. But if it was not, it would return a tuple in an option of the first character and the rest. All of this again makes me think that I could have just done it reverse and process each character one by one without explicitly tracking that state. I needed a way to find out whether a character that was closing a bracket was matching the one that opened it, and I had two lists of these characters and they were ordered by the same kind of bracket. So for example, the square bracket was the third element in both of these lists. So checking if the characters are the same, like they correspond to each other, was basically a matter of checking if the index of them in these lists is the same. So once all of that was implemented, all I had to do is find all the failures, which was basically a matter of parsing each line to an either. Then I would swap that and convert it to an option, so I would only keep the failures as an option, and the list of lines would flat map to that, so I would get just a list with all the failures. Then for each failure I would find its score and sum all that together. You could be more fancy here and optimize this a little bit, because there were only 4 kinds of characters to close a bracket. You could use an enum instead of just a character to track the kind of bracket that you're dealing with. And for example, do a group by on the list of errors, group by the kind of bracket, and then just multiply the amount of each bracket by its score and then sum that together. But in Advent of Code, what I'm focusing on this year is speed first and foremost, so I didn't do that. Especially since I'm not using Scala 3, because it just doesn't work with worksheets very well. Now in part 2 we were actually supposed to look at only the successful lines, but the catch was that they were not just successful complete lines, they were actually just opening some parentheses, some brackets and so on, but they didn't have to close all of them, which is something I had not even considered before. I was just thinking about whether we are closing the right brackets. Thankfully, we didn't need to consider that for the first part. So now, looking at the incomplete lines, we were supposed to basically complete them, so find the right characters to complete each line with, in a way that would keep the brackets balanced as they were supposed to be in the first part. And my idea here was very simple. I would just take the final stack of every line and play it back, but with every character flipped. So instead of opening a specific bracket, I would close it. Initially I thought I would have to reverse my stack to get these values, but then I realized that my head of my list was actually the bracket that I was mostly in. Like, it was the most nested one. So if I were to play back everything till the end, till the outermost bracket, I didn't have to reverse anything. That was already the right order. However, the website doesn't accept arbitrary text in the input. They take numbers instead. So the way we're supposed to return a result would be to calculate a new score, but for these completions instead of errors. And here the scoring system was a little more complicated. We would start with a score of 0, and for each new bracket that we're going to close, we would multiply the current total score that we had and add the value of the corresponding bracket, and then do this just in a loop until the end. So I played back my stack, I mapped each bracket that I was closing to a number, and I did a fold left with that exact logic, multiplying the current score by 5 and adding the current points. Although initially I forgot that I was supposed to multiply anything, so I just summed all the points together. Later I fixed that and that gave me the correct result. But there was one more complication here, because these were scores of each individual line and we were supposed to find one score, and this time it wasn't like the sum of all the scores or not even the highest score, it was actually the middle score. The list was supposed to contain an uneven amount of elements, an odd amount, so the easiest way to find the middle element, like with the middle score, would be to sort all the results. and take the middle element. In this spot, I actually did an off by 1 error. I would take the next element, not the middle one, but eventually I found that and I fixed it and submitted the answer that was correct. For the refactor, I would, as always, create a normal Scala file instead of a worksheet. I made some small refactors to make sure I can pass different kinds of input to my functions and reuse them for the examples and the real thing, and I added assertions. As I mentioned before, I removed these unapply methods for the extractors of openers and closers, and I just replaced that with predicates, so functions that would take a character and return boolean. I also made a map out of the pairs of brackets so that it would be easier for me to find the corresponding opener for each closer. And I did this by zipping the two lists together to get a list of tuples and just used two maps on that to get a map. I also used a similar trick with zipping when I was doing scores for each bracket. So I would zip the list of the characters with a list of the scores and then change that to a map. And because each map in Scala is automatically a function from its keys to the values, I could use that map as a function. Although you have to remember that these maps are not total by default when we treat them as functions, so these are actually partial functions, and normally you would have to check whether the input is included in the keys. You can do that with just treating the map as a partial function or using the get method instead, which would return an option instead of just the type of the elements. Anyway, that was the end of day 10. Day 11 was another very interesting task. We would get another two-dimensional matrix of numbers, and every number would be something called an energy level. We would be given a number of rounds in which we would process these energy levels, and every round would consist of 3 steps. 1. We increase all the energy levels by 1. 2. We find the energy levels that are higher than 9. All the energy levels that were higher than 9 would flash, and this would basically mean all their adjacent energy levels, so basically all the siblings in all directions, including diagonals, would increase by 1. This could potentially make some of the siblings flash as well, so we would repeat the procedure, although a single position could only flash during such a step once, so during the whole round. So once we were done doing all of this and there was nothing left with an energy level greater than 9, we would proceed to the final step of every round, which was setting the energy level of every point that flashed to 0. So given an amount of rounds, we would basically have to transform the input n times using all these steps. And in the first part we had to do 100 rounds and then find out how many flashes in total we had. At first I completely misunderstood the assignment, so I'm not even going to show you my thought process on that. But eventually I settled on something that actually worked. Let's just focus on a single round for now. A single round, which I actually called a step in my code, would take a data object, which is just the map of all the positions and all the values at these points, and it would return an updated value of that data as well as the set of the positions that flashed. First things first, I would increase all the values in that map, and I would pass that to an internal go function. The go function would take this kind of data as well as the set of positions that already flashed within that whole step. So initially we would pass an empty set here. Inside we would find the points that were supposed to flash now. So filtering, like removing from the data all the elements that already flashed and then finding the ones that had a value greater than 9. If this was empty, which would be the case when we've already flashed enough stuff that nothing else had this energy level, we would just return the data and the already flashed points as a result of go. Otherwise, we would take the positions of all the siblings of these flashing points and add 1 to every point at such a position. Here I'm using the map monoid, so basically we have a list on which we map and then we combine all the results. That's what fold map is. And combining results here means using the monoid of the result type, which is a map here. The monoid has an associative operation of combining 2 elements, and for maps, this works as following. It will combine the key set of both maps, basically adding whatever is included in one of the maps, but for every key that appears in both maps, it would use the monoid of the value type to combine these. And because my value type is an integer, it would use that monoid to sum these integers together. So any point that was a sibling of more than one flashing element would have a value that was equal to the amount of of points that were flashing next to it. So if you were a sibling of 2 flashing points, you would have the value 2 here. Later on, we would add this map of updates, because this is what this was, to the data value that we got in this call to the go function. So we wouldn't really replace the values in that map, we would actually add to them. And also we would add the currently flashing points to the already flashed set, so that they would not flash again in the next iteration of Go. And we would call Go recursively. At some point, Go would just return a value because of that first if, and now we would only need to apply the last part of every step, which was to set all the values of the flashing points to 0. So we would take the result of that Go function, the points that flashed, and overwrite the values in the map, in the data map, with zeros at these points. And finally we'd return all these points, the flashing points, as well as the data. So this was all one round, one step, but we're supposed to do 100. So to do 100 steps, I made a list of 100 elements and I folded on it, starting with the original state. Then for every next iteration in my fold, I would call the function step with my last seen state. And I would also accumulate all the points that were flashing so that I could get the amount of these points in every round and sum all of that together. That was the result of part 1. Part 2 was mostly the same, except there was one difference. We were not supposed to do a constant amount of rounds. We were supposed to actually do this until we find a round that passed the following criteria. All of the points in the input were supposed to flash in that round. So to do this, I refactored from my fold left to an iterate on a lazy list, which is basically a stream in Scala 213. And I would iterate starting with the initial state and then updating it, running a step every time. And I would basically do collect first with the condition that the amount of flashing points in that round was equal to the size of the dataset. And when I found that, I would take the index of this plus 1 to get the number of the round. And that was the result of the second part. And this is actually the final state of my code, so I'm not going to walk you through the refactoring process this time. Okay, so I realized that this format was kind of getting boring and difficult to edit because the recordings that I made were very messy and it was difficult to comment on that. So I'll just walk you through the final implementation for each part and the changes that I make to get to the next part and the cleanup afterwards. But I'm not going to show you the actual footage because it's just way too tedious to work with. So here we're on part 1, and as I mentioned, I was going to do depth first recursion. So what this means is that this function would be called every time that I found a possible next point to go to. I would find all these possible points, and if there were some points in here, I would take each of them and add that point to the history, to the current path, and consider what happens if I go with that. So the current path plus that point, how many actual valid paths does that give me? So we would recurse with this, and this will yield a non-empty list. I'm just like toListing and flat mapping to get a larger list. I'm also keeping the current history as a final result, just in case these paths don't end at the end cave, right? So just in case that they don't lead to anything useful, I want to keep the current history because this will be valuable. Like for example, if we are currently at end and we want to go somewhere else to try like end, F, G, end, like this is actually a valid like ending to a path, right? Something like this, starting with something else. We can actually circle back if only end wasn't a small cave. Regardless, whether this is possible or not, I wanted to do this, and eventually you'll see that we filter all the paths by isEnd. So we only keep the paths that end with the end cave. Anyway, back to the recursion. So I would look for the possible candidates, and if there are some, we would recurse trying out all of them. But if there are none, I would just complete with the current history, so the current path. And if I didn't keep the history in the other call, this would probably be lost. This would be a prefix of the path here, but sometimes we wouldn't get that value in the final result, and it does change the result of the whole thing. So I decided to keep it. And to find out where I can go to from a specific cave, I had these two maps. So I had edges by from. This was basically a map of the cave that I am going from and the caves that I can go to directly from that cave. And this is based on the list of edges, the set of edges actually, which I got just from parsing the input. So this was just like from to, we are just grouping on the from value. So that, for example, here we have from end, like these would end up together in this under the end key. As you'll see, here we have CB and BN. So both of these values ended up in that set in the value part of the map. And we would do the same for the opposite direction. So I would just group by the target and basically flip the whole thing. So we can get to the point CB from these points, and we can go to PK just from start, according to going from the right hand side. And then I combine these two maps using the map monoid, which we've already discussed in the previous day, so that I have a huge map of literally all the connections between points. So from the endpoint, I can go to all these points, and vice versa. If we looked up at CB, we would find the endpoint in there, and that would also be the case if we tried any of these. So this allowed me to do something like this, like get or else on the current cave that we are in. If I look up in the map what I can go to from that point as the alternative, like if there are no paths, we would just go set empty. And then we also need to make sure that we don't consider caves that we've already visited, which are small. So that this ensures, like this, minus, and filtering all these elements from the history, the small elements from history, this would ensure there are no duplicates which are small caves. When we call this whole find paths, this recursive function starts with just a path with a single element at the start point. Then we filter the paths by the ending, and we reverse them because, as you'll remember, the history, the first element is actually the end of the path. This doesn't need to happen, like it wasn't actually useful for the solution, but just to have a correct result, something that meaningful. On the outside, when we call find paths, I did this reversal. So all the paths are reversed, now they are in correct order after we called find paths, and to just find how many of them there were, just call size, and this was it. For part 2, there were a couple small changes. First of all, the small caves could be visited twice, but only one of them, so the rest could still be visited once. And also the start and end caves could no longer be visited more than once, even though, at least in my input, the first part wouldn't visit them twice anyway, because their names were lowercase. Maybe this was just an exception in my input, maybe this was a general thing that they didn't point out explicitly. Or maybe I just made the wrong assumption and treated this as a small cave. As I'm editing this, I realized why this was added. This is exactly because these caves are small, and this is just an exception to this rule that you can visit one of these twice. So start and end are exempt from this rule. You cannot go to them twice, even if they are the first small cave that you try to do this for. Anyway, we could no longer go back to end. So once we see end, you just end the path immediately, and you start from start every time, which I did anyway. So to adjust to this change, I'll just show you the changes that I had to make to get to this point. Initially, I just had copy-pasted the whole implementation and made the adjustments, but the end game looks like this. So I replaced my find paths function with count paths. This is essentially the same thing, except I built in the size part in it. That's just so that it would be easier to call this twice for part 1 and part 2. Then I added some parameters to it so that we would allow a single small cave duplicate and also allow going to start and end potentially twice. In case of part 1, we would have this one as true, but allow small duplicate would be false because we don't allow duplicate small caves in part 1. I changed my possible next value, my list of possible next candidates, to start with the result from the map, but then we would also deduplicate it based on the history and the current settings of the duplicates for the small caves. And then potentially we would skip the start point, or we wouldn't in case the start point was allowed. And also on the top level of the go function, if we were at the end point and the start and end points were not allowed, we would just finish at this point. We would just return the path ending with end from the recursive function. Now the two functions that I added, dedupe, it took the history as a list, and this was a function from set to set. And here I had a condition. If we don't allow a small duplicate, or we already have one, we would remove all the small caves that are currently in the history from the proposed values to go to. So basically, if our history already contains two values of the same element, or if we don't allow these duplicates at all, now we would remove the potential duplicates from the candidates. Otherwise, which would only happen in the second part until we found a duplicate small element, we would just let the whole set through. And the other helper function, which was also a function from set to set, it would be much simpler. If we allowed start and end, we would not touch the set at all, just do identity. But if we didn't allow these, we would remove start. I cannot filter end in here because this way we would never actually reach that cave. But as soon as we have a history that ends with the end point, the end cave, we would complete anyway. So given all these changes, I could define helper functions for part 1 and part 2, which were basically calls to count paths, except with different parameters for these booleans. And that's it for day 12. Finally, it's time for day 13. The input for this task was basically two things. The first thing was a list of coordinates on a two-dimensional space. This is nothing new, we've had plenty of these this year. And the rest was instructions on folding something. So what we actually got was coordinates for points on a transparent sheet of paper. We'll get to what the transparency means, but basically for now we can think of this as just coordinates on a piece of paper. And then we were given some instructions on where to fold. So if we were supposed to fold along the y-axis, we would basically have to find all the points that were beyond that line and basically flip them relative to that line on that piece of paper. And if we got a fold along x equals something, we would have to find all the elements past that horizontal position and flip them. So basically if we found points that were on the right of 5, and we had the instructions to fold along x equals 5, we would have to flip them. So for example, something at x equals 7 would end up at x equals 3, because the distance has to be the same, but on the other side of the point at x equals 5. Here we have some visualization of what this would look like. For example, this would be at 3, 0. We're starting at the top, this is 0, 0, and then we have the highest values on the bottom right corner, and the hashes are basically the points where we actually have some points, and the dots are just empty. So this is what the fold would look like. This is y equals 7, so everything below it would be flipped. All these points would be flipped to above that line. And we had a fold along the x-axis. We would flip from the right-hand side to the left-hand side. And the whole transparency, the whole point of the transparency of the sheet of paper is that when two points overlap after the fold, they become the same point because they are basically on the same position now. And the first task was to count how many dots, how many points are visible after performing the first fold in our input. And I'm going to just say this now. The second part basically says you have to fold everything, so perform all the folds and then read what the result is. And the result would actually not be very machine readable, it would be some human readable output of 8 capital letters. So let's look at the implementation. First of all, I parsed the input, which was just a string, into the two things. So first we had a set of all the positions, all the points where we had dots in the beginning, and then we had a list of folds. And the fold would be just either a horizontal fold along the x-axis or a vertical fold along the y-axis. And the parsing was pretty easy. For the positions, we would split by new lines first, and then we would use the string interpolation extractor from scala 213 and above, which we've seen many times in this year, to extract these coordinates. Then I would make it a set because it doesn't matter how many points we have at a specific position. And for the folds, we would again split by the new line character, and we would extract every fold using this string with just a placeholder at the end. And by the way, I got these two things by splitting the whole input by 2 new line characters and ensuring that this has exactly 2 elements. And here I'm using the unapply method on array. This is how this works. This is just pattern matching, by the way. So after parsing, I knew I needed something that would basically perform a single fold. In here, this is called perform. So we go from a set of positions and a fold to another set of positions. And these would be basically after we have performed the fold. Also, it's worth knowing that because we fold from right to left and from the bottom to the top, the sheet of paper becomes smaller and smaller with every fold. So we only need to deal with the positions that are in range between the closest and the furthest of the points from the point of origin of the whole space. Anyway, so I had a pattern match on the fold. And if it was a horizontal fold, I would flip the x value. If it was a vertical fold, I would flip the y value. Both of these functions would operate on tuples of integers. Flip x would basically do this kind of logic. If the point that we're supposed to flip is on the left side of the x value, we would just return that unchanged. But if the point was on the right side, we would do some more complicated logic here. I actually started with something like this. So basically the x here is the point that we are supposed to fold at. So I would subtract from that point, that place where we're supposed to fold, the difference between the x value of the point and the line that we're supposed to fold at. And this actually simplifies because this, let's call this new x. This is just x minus px plus x because we have a parenthesis, so we flip all the signs inside it because there's a minus before it, and this just simplifies into 2x minus px, which is what I had in the end result. And for the vertical fold, I'm actually calling this flip x with my input, but I'm swapping the tuple before and after I call it. So basically I'm calling the flip x function with y first and x second, and I'm getting y first and x second, and then I swap it again. This just flips the order of elements in the tuple. So this ensures that I'm not duplicating this kind of logic, but it might not be the most readable kind of code, so choose your own adventure. And the whole mod, the thing that I got from pattern matching on my fold, was a function from a tuple to a tuple, and I would just map my set of positions to that. Because this is a set, mapping on it also ensures that all the duplicates are removed, so any points that overlap would be deduplicated in here, in this map. For part 1, I would just take the first fold and I would perform that on my set of positions that I just got from my parsed input, and I would take the size of that, and this was it. For the second part, it was a little more complicated because not only did we have to actually perform all the folds, we had to display the output. So to perform all the folds, I would actually take the list of folds and get this. I would perform a fold left, starting with my initial positions, and then I would perform every fold as we go. So this would return the updated set, and this would be passed to the next perform call. And then I called show, which is how I display the output. So let's look at that. To display the output, I needed to know how large it's going to be. So I would check the maximum x value and the maximum y value by just mapping on the set of positions and taking the max first and the second field of the tuples. And the beginning would be zeros every time. So I would map on the vertical values first and the horizontal ones, so that this would give me basically rows, and the mapping on the x values would be columns in this output. And if the set of positions contained the given point at x and y, I would put a hash. Otherwise, I would put a space because dots, as I found out, were just not readable enough. And for every row of entries, I would use make string to combine all these strings into a single line, and then I would make string on all of that, but combining with the new line character. So I would get some human readable output. In the end, this is what I got. Not very readable, but this worked. And here I'm actually using a hack to perform my assertions. I needed to make sure that the spaces in here don't get removed by my editor. I have a setting on where this automatically trims trailing white space in every line. So I'm inserting the spaces using string interpolation, just like that, and it actually works. And this is how I'm comparing the results using a string-based comparison. And as a piece of trivia, this is how I did it for the example input, which actually had something close to a 0, I guess. This one didn't require any trailing white space because all the hashes are in the last column, so there's nothing after them. So this was a pretty fun exercise, but the fact that I actually was supposed to read what this says took me quite a while, because initially I didn't really understand the assignment, but eventually I was actually happy that I could use the fold left function, because perform here has the perfect shape for something that you would pass to fold left. You have the current state and you have the fold that you're supposed to evaluate next. Of course, again, this could be a traverse with state, but this shape was so nice and fit the problem description so well that I just used this. And using the state monad would probably complicate the whole solution much more than anything else. So this is it for day 13. Thank you for watching the episode. I hope you liked it. You know what to do. Just leave a like, subscribe, and I'll see you in the next one.